Hello everyone, this is Amit Prambhat, a professor for CSC 208 at Ridge Community College. Today we are going to continue on lecture series for discrete mathematics around combinatorial proofs. So we'll move on today to the next slide, which is around symmetry theorem. Let's look at our first major identity. N choose k is equal to n choose n minus k. Algebraically, this is trivial to verify by looking at the denominators of factorial formula. But let's prove it combinatorially. Suppose you have a pool of n students and you want to select a committee of k students to work on a project. Alternatively, you could also accomplish this exact same task by choosing which n minus k students to exclude from the committee. Every choice of a committee uniquely defines choice of non-committee members. Thus, the two counting process must yield exact same results. Subsets as binary strings. Why is the total number of subsets of a set of size n equals 2 raised to the power of n? We can prove this by creating a bijective mapping to binary strings. Imagine listing the elements of your set in a fixed order. For any subsets you want to construct, you can represent it as a binary string of length n. Each bit in the string acts as a switch. It is a 1 if the corresponding element is included in your subset, and a 0 if it is left out. Since there are exactly two choices, 0 or 1, for each of the n positions, there must be 2 to the n total binary strings, and thus 2 to the n total subsets. Pascal's rule of recurrence. Pascal's rule gives us a recursive way to compute binomial coefficients. N choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k. Let's prove this combinatorially. Suppose we want to choose a team of k players from a pool of n candidates, and let's pick one specific star player, say Alice. We can partition our selection into two disjoint cases. Case 1 is Alice is on the team. In this case, we only need to choose k minus 1 more players from the remaining n minus 1 candidates. Case 2, Alice is not in the team. Here, we must choose all k players from the remaining n minus 1 candidates. Summing these two cases gives us the total. Let's talk about Blaise Pascal. While the famous triangular array of numbers bears his name in the Western world, Blaise Pascal was far from the first to discover it. Mathematicians in India, Persia, and China had utilized this triangle centuries before Pascal's birth in 1623. However, Pascal's genius lay in his formalization. In his treatise on the arithmetical triangle, he united these coefficients with early portability theory, showing how they could be used to solve gambling problems and divisions of stakes. His work helped transition combinatorics from a series of scattered puzzles into a cohesive mathematical discipline. Constructing the triangle. Constructing Pascal's triangle is it's simple, but it leads to incredibly deep properties. We start with a single 1. at the apex, which we call row 0. Each subsequent row is generated by placing a 1 on the outer boundaries and calculating every internal entry as the sum of the two numbers directly above it diagonally. This geometric addition is literal physical representation of Pascal's rule. The values along the nth row correspond exactly to the binomial coefficient for a set of size n. Starting from n, choose 0 up to n, choose n. If we sum the entries across by horizontal row n of Pascal's triangle, we discover an elegant pattern. The sum is always perfect power of 2, specifically 2 raised to the n. Let's think about why this must be true. The entries in row n represent the number of subsets of size 0, size 1, size 2, and so on, up to size n. When we sum these entries, we are totaling the number of subsets of all possible sizes. As we proved earlier, the total number of subsets of a set of size 2 is to the n. Thus, the row sum must equal to 2 to the power n. Divisibility by primes. If row number p is a prime number, then all entries in that row, excluding the ones, are divisible by p. And then we have 3 rows with numbers divisible by the row number. Here's a remarkable number theoretic property hidden in the triangle. If the row index p is a prime number, then every single internal entry in that row, excluding the boundary ones, is evenly divisible by p. Let's look at the row 5. The internal entries are 5, 10, both are divisible by 5. In row 7, we have 7, 21, 35, which are divisible by 7. However, if you look at composite row like 8, we find 28, which is not divisible by 8. This property is deeply connected to Fermat's little theorem and forms the basis of several modern primality testing algorithms. Visual fractal patterns. What happens if we take Pascal's triangle and color each cell based on whether its value is odd or even? In other words, we evaluate the triangle modulo 2, coloring odd numbers black and even numbers white. As you can see in the diagram, a stunning geometric fractal emerges. The Sierpinski Gasket is its name. The self-similar mathematical structure consists of smaller triangles nested infinitely inside larger ones. It reveals that deterministic arithmetic rules, when applied iteratively, naturally generate complex organic fractal geometry. Now let's talk about multisets and multi-choosing. In the next section, I'll end this section for now. Thank you.